So we're looking at more curve sketching questions here. So our function is 1/4 of x to the power of 4 minus 3x cubed. So our first step is always to first find the first derivative and set it equal to 0, because we usually want to find the turning points and determine their nature. So derivative there, we factorize and we get from x squared, x must be equal to 0, and from x minus 3x would equal to 3. Second derivative is going to be pretty easy to find, so we'll get the second derivative and we'll test it. So when x is equal to 0, well, it's pretty easy, y is equal to 0. Our second derivative gets its the first that's equal to 0 as well. So we've got a horizontal point of inflection. So there's our first point there. X 0, 0 is horizontal point of inflection. We get our y value for x is equal to 3 at minus 6 3/4, and so we get that 6.75 there, and our second derivative is greater than 0, so it's a minimum. So there's our two turning points. Points of inflection, well, we get our second derivative equal to 0. We know that 3x, we get our derivative and factorize, 3x comes out, which means we get x0 and y is equal to 0. Well, we've already just proved that was a horizontal point of inflection. So we also get this situation where x is equal to 2 and y would be minus 4. Again, we test our concavity either side. So at 1 it was negative and 3 it's positive. So we get a sign change, so the concavity is changing at 2 and a point of inflection is this. So we've got 2 points of inflection. I'm going to sketch the curve between those two values of the domain of x. So this is where we substitute those in and we get our y values. Not pretty values, but there you can see those there. Minus 1.5, we get 4 and 41 over 64. And at 4.5, we get 11 and 25 over 64. Which are not very nice values. We're showing our horizontal point of inflection at 0, 0. Our minimum turning point there at 3. And then we can, again, read off our graph, or we can solve it analytically for what values of x is the curve concave down. So you can see it's concave down between those 2 points. So it's really working out where the second derivative is less than 0. Again, analytically we can solve it that way, or read it off the graph that's between 0 and 2. In question 4, a little bit different this time, because we've got a function here, and we're looking to manipulate it a little bit. So we've got this part of the function, x is greater than or equal to 0, so that's only where x is positive or equal to 0. Starts at 0, 0, has a maximum turning point at 2, and a point of inflection at x is equal to 4, and is asymptotic to the line y is equal to 1. So that's what that looks like. So what's the value of the function of x for which the first derivative is equal to 0? Well, we can read that. We know that it's equal to 2. The first derivative greater than 0, well, we can see where's the curve rising. That would be between 0 and 2. There. And we should probably have equal to 0 as well, because at the point x is equal to 0, and x is defined for x is equal to 0, we know it's rising. And where's the second derivative greater than 0? Well, the curve's concave up. We can see where it changes concavity. It's concave down all the way there, and we're told it changes concavity. So at x is equal to 4 and greater than 4, sorry, x is just greater than 4, changes concavity at x is equal to 4, it's concave up. So that's what we're looking at there. State the limit as x approaches infinity, the function of x. Well, as x gets larger, what's happened to the function? Well, the function starts to approach the line y is equal to 1, so the limit of the function must be 1. And then suppose the curve is sketched, represents part of an odd function. Sketch the graph of that function there. So we know if it's an odd function, it has point symmetry. It has point symmetry there, so it's going to rotate around the x-axis. So the origin, not the x-axis. So we have to draw up our asymptote there, and it rotates around. So the curve would look exactly the same, but rotated around and in the third quadrant. So that's what an odd function would mean. It rotates around that origin, so it would look exactly the same. So there'll be different type of question, but again, calling into the ideas of what happens for curve sketching. What do we have to look at? First derivative, second derivative, things like asymptotes. We have to, so what's the gradient doing there? Also the idea of an odd function. It all comes into play to be able to sketch curves and with this in sketching curves here using calculus.